Oh yeah. So the reciprocal in the complex plane maps the outside of the unit circle into the inside of the unit circle. So the norm of the reciprocal is equal to the reciprocal of the norm, which means if I'm outside the unit circle, after the mapping, I get inside of the circle, right? Okay. So we can do this for any combination of spatial and temporal schemes. And one of the things we found always find is that in combination with an explicit scheme, the stability, in order for me to have stability, I must satisfy the Cfl condition. That is, the ratio between delta t and delta x has to be less than a certain criterion, less than a certain limit. That is a function of the spatial and temporal discretization scheme. So that is commonly known as the Cfl condition. So for example, if you use the upwinded spatial discretization combined with the forward Euler, or if you use upwinded spatial discretization combination with Runge-Kutta schemes, you would always have a Cfl condition that limits your ratio between delta t and delta x. And that limit depends on what scheme do you use. It is equal to 1 if you use first order backward difference in space in combination with forward Euler in time. Okay, question? Yeah, it is known for most spatial and temporal schemes, right? And okay, so for example, for this equation, plus a big U times partial U partial x equal to 0, you need a big U in front of the delta t and delta x, because this is it's like a unit conversion between the time and space, right? Yes. Yes. Oh, if you so good. So if you have a scheme that utilizes more than 2 sequential time steps, you also use the same von Neumann stability analysis, except for you get a relation between u hat n plus 1, u hat n, and some other, for example, u hat n minus 1s. So you get a relationship not between 2 consecutive time steps, but like more time steps. And then if you write down, so for example, if you get 3 consecutive time steps, then you can write down u hat of n plus 1, u hat of n as a matrix times u hat of n, u hat of n minus 1. And the matrix is always going to be, so let's see, this is going to be 1, 0, right? Because u hat of n is equal to u hat of n. And these are from the derivation. What's next? Can somebody point out, after I write this matrix, what? Exactly. For that 2 by 2 matrix, you look at the eigenvalues. If this matrix has an eigenvalue greater than 1, unstable. If all the eigenvalues are within the unit circle, stable. What if you have 4 consecutive u hats? 3 by 3 matrix. If you have 5 consecutive terms, it's a 4 by 4 matrix. And again, look at the eigenvalues. So all the Cfl conditions are obtained by analysis like that. Yes? Yes, that condition does not exist for some implicit schemes. for some implicit time stepping schemes. I think somebody proved that for explicit schemes, that condition, there is always such a condition. It's impossible to get unconditionally stable schemes for explicit integration schemes. But for implicit schemes, you can have something like that. It's always stable. Yes? Yes? Oh, okay. So K is the frequency in the discrete space, right? So if you want K to be the frequency in the continuous space, you need to multiply delta x. So you need ijk times delta x in order for K to have the right unit in the at the frequency in space. Here, if you interpret K as the frequency as like the K in the discrete Fourier transform, which means like it's a grid by grid type of frequency, then you don't. Yeah. Yeah, a lot of people. I mean, I didn't put delta x just to reduce some clutter on the screen, but like a lot of books actually put a delta x on it. Which one? Yeah, this is the space of A. It's real of A, imaginary of A, right? This is I'm trying to plot this multiplicative factor. Yeah, I think I'm missing a delta t here. I'm trying to plot the multiplicative factor that gets you from the current time step to the next time step. Any other questions? Okay, so we have said that we want this matrix to have eigenvalues less than 1. In other words, we want our discretization of the PDE to be stable. If you introduce the perturbation is going to decay over time in our numerical scheme, right? That works not only for linear equations but also for nonlinear equations. The exception is that for nonlinear PDEs, we need to linearize the PDE in the area equation. I mean, the assumption is the area is sufficiently small so that like the difference between analytical solution, exact solution, and numerical solution can be linearized. So let's say my u hat of n plus 1 is equal to a nonlinear operator of u hat of n. So this is and if you put the analytical solution in, I would have a truncation error tau. So if you subtract these two equations, the left-hand side becomes e of n plus 1. And the right-hand side becomes, let's say step n, becomes the nonlinear operator operated on the analytical solution minus the nonlinear operator operated on the numerical solution plus tau of n. Because this is a nonlinear operator, you cannot just say the difference is just n operated on e to the n. But if the difference between un and u hat of n is small enough, you can perform a Taylor series expansion to this n. And with the Taylor series expansion, we can approximate this as partial n partial u hat of n times the difference between un and u hat of n, which is e of n plus tau of n. And now we want this derivative, this numerical, the Jacobian of our numerical approximation to have eigenvalues in the unit circle. All right, so that's basically how we apply the same analysis to nonlinear equations. Any questions? Yes? Oh, that's a very good question. So yeah, so the error of linearizing the nonlinear operator can be, I mean, if you want to be exact, you may have another term that is I use the tau maybe gamma of n, that is as a result of linearizing this. But as long as the partial n partial u hat is stable, the effect of this wouldn't really accumulate. It would decrease over time to keep the e to the n to be bounded without going to infinity. All right, any other questions? If no, we are going to go into finite volume after, let's say, a 5 minutes break. All right.